Hi, in this video, we want to take a look at classical regression in the time series context. All right, so a better way to describe what we're going to do in this video is that we're going to take standard linear regression models and we're going to pull in lag variables. All right, so lag variables are, previous observations of what we're interested in predicting, or another time series that's related to what we want to predict. We're going to be pulling in, and so we're going to be incorporating time series and linear regression in this situation. And looking forward, we're going to be moving into autoregressive models, but we're not going to quite touch that yet. Right now we're going to start with linear regression, which is a more familiar to more people, and then we'll move from there. All right, so we're going to be working through an example from time series analysis and applications. Here are the authors' names, and here's the GitHub page. Here you can get information about the package, ASTSA, and the textbook can be downloaded for free by UCF students. All right, so if you want to install the package onto your machine, now CRAN does have, the R repository CRAN does have ASTSA on there. You can download it very easily, standard way. If you want the most up-to-date version that hasn't even made it to CRAN yet, you can use the install GitHub function to accomplish that. Now here I'm going through and I'm setting it up so that I have fewer digits printed out, and I want to, that's what the digits option does, it limits it to 3, actually sometimes it'll be 4. And then the larger the SciPid number is, the less the system will want to print scientific notation. I prefer just the regular numbers. And here I'm just clearing out any old items from my workspace before I get going on my code. Now don't do this unless you want to lose whatever is on your workspace. You'll delete it all. All right, so let's actually talk about the topic at hand. All right, so let's say I've got a time series over some time instances, and we believe that my time series X is influenced by other time series that in this video we're going to call Z. And notice that there are multiple time series that are influencing X. All right, so what we want to do, we want to build a linear regression model using these time series as the independent variables, as the predictor variables. And so my model is going to be, standard linear regression model. X of t is equal to intercept plus coefficient times input variables. And then I'm going to have the randomness will be contained in one term in the entire model. And we're going to assume that that randomness is IID normally distributed with mean 0 and constant variance for all our observations. So it's going to be constant with respect to time and with respect to the X values also. Also, we're making the assumption in this setup that there are no autocorrelated errors. In future videos, we'll talk about autocorrelated errors and ways to get around that. But for now, we're just assuming that autocorrelation aspect is not an issue. Now, realistically, this assumption of IID normal and constant variance is unrealistic in most situations in real life, but it works for a lot of models. And for now, we're just going to, when I say it works for a lot of models, it works for a lot of real life situations, even though realistically, if you thought about it, if you're honest about it, it probably doesn't hold, but it's usually close enough for real life. All right, so let's talk about estimating a linear trend. So let's go ahead and look at the situation where I have one other time series that I'm interested in. So I've got one input variable. And in this situation, we're going to be talking about chicken price over these months. All right, and if we look at the visualization, so whenever we're doing regression, our plots are our primary tool to know if I have a good model or a bad model. All right, so what I can do is if I look at this, I see the blue trend, or I see the blue plots going upward with respect to time. And so I'm like, there is an overall trend. So let's go ahead and find it and start modeling statistically. All right, so obvious upward trend in the series. And so let's go ahead and use linear regression. And here, what we're going to do, we're going to say that Z is the actual time of interest, where we're going to have, like for March, so this should, March 2002 would be 2002.25. And so we're going to represent the month as a fraction of a year. And this should be an O. The current year of me making this video, of making the script, 2022, not 2002. And that is a typo on my part. All right, and we're going to go ahead and assume that our random term is IID normal with no odd correlated errors, and we have constant variance with respect to time, with respect to the X variable. All right, well, so here is my model. Here's the mathematical form of my model. Now, that doesn't tell me what are the coefficients. All right, I'm saying I've got an intercept and I've got a slope. All right, well, what are they? All right, so what we're going to do is we're going to use ordinary least squares. Now, honestly, there are infinitely many ways that I could come up with an intercept and a slope. Tons and tons and tons of ways. The one that is by far the most commonly used is what's called ordinary least squares. What we're going to do is that we're going to take our data and I'm going to find the intercept and the slope that minimizes the sum of squared errors. All right, so, oh shoot, this should be a WT squared. This should be squared. So here is the error between my model. So this is the modeled value, and this is the observed value. And so when I subtract, that's the error of my model. When I square it, that is the squared error, and then I can add it all up. What we're going to do is this, for this overall sum, I'm going to minimize with respect to the intercept and the slope. Okay, and so how am I going to do that? Standard way in calculus is I've got a sum of degree 2 polynomials. And so what I'm going to do is I'm just going to take a derivative, set it equal to 0. In this situation, the minimum is going to be where the derivative is equal to 0. And so, and how to convince yourself that the minimum is automatically where the derivative is equal to 0 is realize that if I was to expand this out, do the quadratic, and then add up all the terms, and then get the intercept and the slope by themselves. If I think about that for a moment, I realize that overall, this is going to be a degree 2 polynomial on those two things. And so it's either going to be concave up or concave down. And if I was to get farther away from the observed values, let's say I start plugging in model values of plus or minus millions, something like that, I know that my overall error would increase. Therefore, the minimum is going to be where the derivative is equal to 0. I don't have to use the second derivative test. All right, so here, what we're going to do, I'm going to go through, I'm going to find where the partial derivatives are equal to 0. And if I sit down and I solve that, the one I'm going to do first, because I've already worked this out, I already know this from when I was a student studying this, the one that's going to work out first is going to be the slope. All right, I'm going to work out the slope, and then after I figure out the slope, I'm going to start focusing on the intercept. And it works out that in every single ordinary least squares model, it's always going to pass through the point of averages. And so you'll notice that here I have X bar, I have Z bar. If I take the average, the point of the averages, so X bar, Z bar is the point I'm talking about, then that will always be on my ordinary least squares model line. Okay, well, I can use that very easily to get an equation to work out the details. All right, and so when I work this all out, I'll get this formula. Notice that this is the covariant, the sample covariance between X and Z, and then the numerator and the variance of Z. All right, so in this situation, we get an estimated slope of 3.6 and a standard error of 0.08. So this is statistically significant. And here's some information about the data set from the ASTSA package. All right, so how do we get this? So first I'm going to load my data. And then to just visualize, to give myself intuition on what's going on, I'm going to plot the trend of the time series. And so here, yep, we can see that there is, visually, it looks like there is a trend going on. All right, so let's go ahead and create a linear model off of this. So I'm using the time function in the stats package to get the time component of the time series. So the chicken data set is a time series data set. And because of that, it has a time part of it. So I go ahead and just, grab that with the time aspect. And then, my formula is that chicken depends on the time. And so now let's go ahead and take a look at that model after I built it. I'm calling it linear model chicken. And so we can see that we have, about 3.6 for the slope, and it is statistically significant. Here's my R² value. And here is the p-value for the F statistic. And the F statistic is going to have a direct matching with this one because it's a simple linear regression. All right, so let's go ahead and just look at this another way. Let's go ahead and use the time series plot from the ASTSA package. And let's go ahead and impose the regression line that we just found using the AB line function. And so we get a similar plot. We don't have the bands around the estimated model, but still pretty good. All right, now we can go ahead and extend this to multiple linear regression. All right, so previously we just had one predictor variable, that was the time. And now we want to make things more general. We want to be able to pull in more variables for our prediction. All right, and so what we'll do, we'll set up so that we'll have more predictor variables. And here I'm going to express it to simplify the notation. I'm going to express all of the input variables for a given particular time as a vector. And notice that I'm including a constant on here. And then we're going to have corresponding coefficients, and I'm going to represent all of the coefficients as a vector. Now, the textbook author does not put an arrow on top of vectors. This is common, but you will notice that there is kind of like overlap in the notation. You're going to have to just know from context what the author is talking about as you work through the book. All right, so here, what we're going to do is I'm going to say that the model is very similar to what we saw before, but now I have more predictor variables involved. I have the intercept, and I have the normal term. And to make it a little bit more compact, let's use some vector multiplication to make this a little bit easier for us. And things will work out exactly the same way as before, except for my model is just more complicated. And once again, I forgot that exponent too. All right, so now how do I find the coefficients of best fit? Once again, I can take derivatives. Also, it's possible to use matrix algebra and projections to do this. I think that's a little bit slicker way to do it. If you look at my linear models videos on my YouTube channel, you can see me go through all those details. But either way, you're going to get the same result. And we're going to get something called the normal equations. All right, so the normal equations are basically just what I get from working out the details of the minimum for the coefficients. And just, everything just works out exactly the way we want it to. All right, so it works out that the ordinary least squares estimate of the coefficients are unbiased, and they have the least variance of all unbiased estimators. This is called BLUE. All right, so BLUE stands for Best Linear Unbiased Estimator. All right, so it's a linear equation. We're trying to estimate the coefficients. We're estimating the coefficients. Unbiased means that the expected value of my estimated coefficients is going to be the actual value I want it to be. So it's an unbiased estimator. And best means that it has least variance. And this is called the Gauss-Markov theorem. All right, so ordinary least squares estimates, the coefficients are unbiased, and they have the least variance of all unbiased coefficient estimators. All right, so remember, we could estimate coefficients in infinitely many ways, but we choose typically this ordinary least squares method because we have these nice properties. It's unbiased and it has the minimum variance of all unbiased estimators. Also, we have a lot of other properties that aid us in terms of like hypothesis testing and other aspects. But the expected value is what I want it to be. And this is vector notation, by the way. The covariance is well established, easy to compute. And we're going to use the C matrix in a little bit. All right, so to estimate the variance, we have a couple of different ways. The first one we're going to go over is the unbiased estimate of the variance. And that's just we're going to call that the mean squared error. I'm going to take the sum of squares error, which we saw before, which was what we were minimizing on. And then we're going to divide so that it's very similar to an average. It's not quite an average, but we're going to go ahead and call it the mean squared error anyway. So instead of dividing by n, I'm going to divide by n minus the number of parameters. And it works out that the expected value of this, of s sub w squared, the expected value is equal to the variance of that error term that we have in our model. All right, so we have an unbiased estimator because the expected value is equal to what we want it to be, what we're trying to estimate. Now, the distribution of the coefficients, when all of the assumptions hold, so when I have independent, identically distributed, and I have the normality assumption, then the coefficients will have a t distribution. All right, so when I take an individual coefficient, and I take the estimated value, subtract off the true value, divide by our estimation of the variance, and then the square root of the term from that C matrix up above here, then this is going to have a t distribution. And frequently, we will use this in hypothesis testing. I personally, professionally, will use this for feature selection also, for choosing which variables to omit from a model. All right, so as I'm going through and building my model, if I have, let's say, 100 different predictor variables, I probably don't want to use all of them. I only want to use the best model possible. And so some of my predictor variables are going to be in my final model, some are not. So what we're going to do, we're going to talk about comparing two models. I have what I'm going to call the full model and then the reduced model. The full model is the model that has all the predictors I'm considering at the time. The reduced model has some of the full model's predictor variables have been removed. Now, something that's important about this, in this setup, all predictor variables in the reduced model are also in the full model. All right, so all the predictor variables in the reduced model are in the full model, but some of the predictor variables in the full model are not in the reduced model. Okay, and so what we're going to do is, by setting up things this way, I get additional statistical tools to compare the two models. And this is why we like to do full versus reduced in contrast to other methods we could do for feature selection. All right, so what we're going to do, I'm going to take a subset of my predictor variables, and I'm going to come up with a new model. Now here, basically, I'm repeating what I had above in the video. And the main thing is just know that I have fewer predictor variables and the subscript for the index has changed. There isn't an exact matching. And I'm being consistent with the author. If we wanted to be truly mathematical, we would have had subscripts and it would have gotten confusing. So they chose to just make the notation simpler. But this first predictor variable may or may not be the first predictor variable in the full model. This second predictor variable may or may not be the same second predictor variable in the full model. We don't know. All right, so what we're going to do, we're going to run ANOVA, analysis of variance, to compare the full versus reduced models. All right, so in this situation, when I have the full and reduced models and I'm running ANOVA, I'm asking myself, are all of the predictor variables not in the reduced model, are all of those coefficients equal to 0? So my null hypothesis is that all of the predictor variables that are not in the reduced model, their coefficients are equal to 0. If their coefficients are equal to 0, that's equivalent to the predictor variable not being in the model. The alternative hypothesis is that one or more of these coefficients is not equal to 0. Now notice that this hypothesis test does not tell me which of these coefficients is not equal to 0. It just says one or more. Could be all of them. It could be only one. We don't know. We have to dig in deeper. All right, so our test statistic for the ANOVA is going to be the F distribution. We call it the F statistic, and we're going to be using the F distribution. So all ANOVA tests use the F distribution, and this is how we compute my test statistic. I'm going to take the sum of squares error of the reduced model, subtract the sum of squares error of the full model, divide by the difference in the number of parameters. That's going to be my mean squared regression. And then I'm going to divide by the sum of squares error, divide by n minus the number of parameters, and that's my mean squared error that we saw earlier. And so it's going to work out every single time that the sum of squares error of the reduced model will always be greater than or equal to the sum of squares error of the full model. The full model has more flexibility. It will, in terms of error, it's going to fit more closely to the data. Now, that may be good, that may be bad, can overfit. That we frequently like reduced models to protect us from overfitting. But the full model will always have a smaller sum of squares error no matter what we do. All right, now, if there's not a big difference, if the sum of squares error reduced is very close to the sum of squares error for the full model, then really the extra terms, the extra complexity in our model isn't worth it. And so we would prefer to use the reduced model. All right, so roughly speaking, if the difference in the sum of squares error is big, I want to use the full model. If the difference between the sum of squares error is small, I want to use the reduced model. All right, so under the normality assumption, so something about ANOVA. ANOVA uses the F distribution. The F distribution must rely on the chi-square distribution, which relies on the normal distribution. So the normal assumption must hold for the ANOVA test to be coherent. If the normality assumption doesn't hold, if it doesn't fit our situation that we're modeling on, then I can't trust the p-value I get from my ANOVA test. The F statistic is still informative, but the p-value is not reliable. But everything else in the buildup of this leads to the F statistic. Basically, the bigger it is, the more likely I will be to reject the null hypothesis in favor of the alternative. And the alternative is that one or more of the coefficients are not equal to 0. And here is the ANOVA table for the situation. And this is a little bit modified from the textbook, but you know, I've got my degrees of freedom. I have my sum of squares. Divide the sum of squares by degrees of freedom, and then take the ratio of the mean squares term. All right, so what happens when I'm in R and I put a model straight into ANOVA but I don't have a second model. So notice that when I was talking about ANOVA a moment ago, I was talking about putting 2 models into ANOVA. If I only put in 1 model into ANOVA, in fact, I still have 2. It's just the other one is like a default model. It is the constant model where none of the input variables have a non-zero coefficient. So in that situation, we're saying that my target variable can be added, from the point of view of the available data, can be best modeled with just a constant value, that there's no relationship between my input variables and my target variables. All right, so the constant model, I'm just saying that my x sub t is equal to a constant, and all my predictor variables are useless for this purpose. The alternative is that one or more of these coefficients is not equal to 0. Now, the ANOVA does not tell me which coefficient is not equal to 0. It just says one or more. All right, so the coefficient of determination, r squared, we use that to represent the proportion of variance accounted for by our full model. All right, and so here, if I'd say SSE sub 0 is that constant model, here's SSE of the full model, and then divide by constant model SSE, then this r squared gives me a measurement of the proportion of the variance accounted for by the full model. Now, we can do this full reduced model process to go through, and I could start with like a constant model and add a variable. So then I have one variable and constant to compare, full and reduced. Then from there, I could add another model to whichever one I choose, and then do full reduced comparison and grow the model in a stepwise forward selection manner. Another thing I could do is I could take a full model, eliminate a predictor variable, and do full and reduced framework. And then if I choose to, remove another variable and do full reduced framework to see if I can keep eliminating variables down to a simpler model. We want the simplest model that gives us as much informative value as possible. Now, a little bit ago, I talked about the mean squared error as an unbiased estimator of that variance term on our normal, the normal aspect of our model. Now, that's not the only way we can estimate that variance. We could also use the maximum likelihood estimator. All right, so the maximum likelihood estimator is going to be the sum of squares error divided by the number of observations. So this will maximize the likelihood. Now, this will be this is a biased estimator. This will estimate overall a little bit low. But if I have a large number of data points, it's not going to be a big difference either way. From a theoretical point of view, there's advantages to maximum likelihood estimators, and there's advantages to unbiased estimators. You have to just kind of choose which one you want to use when you estimate your variance. Now, Akai's information criterion, what this does, this gives us a way of comparing multiple models. All right, so what we want to do, we want to take a look at how well does the model fit the observations, but also I want to consider, is it a complex model? And I want to kind of weigh the two. I want model fit and complexity kind of simultaneously balanced to see what's best. And one way to do this is Akai's information criterion. All right, so to do that, we're going to take -2 of the log of the maximum likelihood from the model plus 2 times the number of parameters. And in this situation, this works out to be the log of that maximum likelihood estimate of the variance plus this fraction if I work out and fit through all the details. All right, so this term addresses model fit, and this term is a penalty for the complexity of the model. All right, so what we want the smallest value possible off of this. Now, if you look through the research, you look through the textbooks, you look through different softwares, there are a ton of slight nuanced different ways to compute AIC. Just make sure you're using consistent software, that is consistent platform and consistent function when you compute AIC. Different packages in R are computed differently. Different platforms like SAS, Python, R will compute AIC differently. Make sure you're being consistent. Just, don't, go and use like Python stat models and then use R, base R AIC and try to compare them to each other. It doesn't work out that way. How we're going to use AIC is if I have, let's say, 5 different models, I'm going to pick the model that has the smallest AIC. Now, it works out that there is kind of a biased aspect to this, the standard AIC. So we have bias corrected AIC, so AIC corrected, and here you'll notice that we have an adjustment on that penalty term. There's also the Bayesian information criterion. The Bayesian information criterion has a larger penalty for the number of terms. It puts a greater penalty on the complexity of the model. So here, in general, BIC will favor simpler models more than AIC. All right, so BIC tends to do well at getting the correct order in large samples, so of getting like the size of the model that I want, while corrected AIC tends to be superior when I'm dealing with a small sample size and the relative number of parameters is large. All right, so let's go ahead and look at an example involving mortality, pollution, and temperature. All right, so somebody took some data that involved, I believe it's cardiac mortality, time, that trend aspect, temperature, and pollution particles. And they wanted to study, using linear regression, the relationship. Okay, well, what they did, they went through and they considered several models. They considered the constant model. They considered the model that just had time. Notice that there's no temperature, no pollution considered. Then they considered also adding on a temperature aspect, and they considered a quadratic term for the temperature, and then they considered putting on particles, pollution particles, onto the model. And so they had 5 models that they considered, and then they started exploring. Now, how did they choose these particular 5? This comes from just like looking at the data, subject matter knowledge, looking at the data visualizations and the statistics, and going, I feel that time is the most important, then temperature, but maybe there might be a curvature in the temperature, and then particle. Maybe particle's important, but I'm not, this one's I'm the least confident about. So that one's the last one to get considered in the system. All right, so let's go ahead and run through the example. Let's load the data. Here we have to load 3 different data sets. So I'm using the data function to load 3 different data sets into my system. And CMORT is the cardiovascular mortality. Let's look at the time series plot. All right, we definitely see a trend. Now, temperature, we definitely see, a periodic trend also. Now, let's look at the particles, and I feel like there is, once again, a periodic trend. So, so let's try to pull all these into one model. Now, here, what we're going to do, we're going to try and plot everything together. So here, to do this, I just put all my time series in the cbind function. If you use data frame instead of cbind, you will lose the time series aspect of the object. So be ready for that. You can tack it on using the time function that I talked about earlier. But if I went straight data frame with these 3 as is, I would lose that the time attributes. And so now we can see the relationship, and looking at it, there might be something going on. So let's go ahead and dig in. Let's study it. Let's figure out what's happening. Now let's go ahead and do a scatter plot matrix to see if we see something else. All right, so when I look at mortality, I do see kind of a downward trend with temperature, but there might be a little bit of curvature here. Maybe. When I look at mortality, you know, there might be an increasing trend, but this also kind of looks like a cloud. So I'm the least confident in the particles, and I really don't see something between temperature and particles, visually at least. All right, so let's actually run the regression. This is how the authors did it. But I did modify a little bit from the authors in that I put everything into a data frame to make things just a little bit cleaner. Then ran it. And so here, first and foremost, my F statistic says I have something informative in my model. Doesn't tell me what, but one or more coefficients is useful. And then when I look through here, I conclude that all of the coefficients are statistically significant. I feel like the full model is a good choice. Here we can see it in another way. Now you'll notice that I have different p-values here and here. That's because these are technically different ANOVAs. Here, this is asking, should this one coefficient be removed? The one down here is asking, given that we have the constant model, should I add trend? Yes, we should. Given that I have constant and trend, should I add temperature? Yes, I should. Given that I have constant trend and temperature, should I add the quadratic on temperature? Yes, I should. Given that we have constant trend, temperature, and the quadratic, should we add particles? Yes, we should. So this is asking, should I grow the model? This is asking, should individual coefficients be in the model? This is a sequential growing or sequential reduction of the model, however you want to look at it. And so here we can run our ANOVA using the AOV function. And this compares the full model to the constant model. And we can fit our AIC and our BIC. And we want these to be as small as possible. Now, I cannot compare AIC to BIC. I cannot compare corrected AIC to either one of those. These are for comparing the same statistic between different models. Here is a manual calculation of corrected AIC. Now, for me, I wanted to go through, I want to compare the models. I wanted to get the AIC, the BIC of each model, and then take a look at what's going on. So what I did, this is not in the textbook, I created a list of linear models going from full model all the way down to the constant model. And I'm going in the order that we talked about previously. Now the NA action, this is set equal to null. This will help preserve the time series features for when I run other functions on the linear model. So when I'm working with time series data in my linear model, I want to put NA.action equal to null if that's appropriate for my missing value handling. And so now I just want to print those statistics, the AIC, the BIC, log likelihood, degrees of freedom, all of that. I'm going to put all of this stuff into a data frame. So I have a model, the number of parameters, including the intercept, degrees of freedom, log likelihood, AIC, BIC, like that. All right, so here I've got them all together. Now, in log likelihood, we want it to be as large as possible. AIC, we want as small as possible. BIC, we want as small as possible. All right, so, and here I'm hitting the sort function just so it's a little bit easier for me to find what it is I actually want. I'm using the sapply function to iterate the log likelihood function on the entire list of linear models. And so we can see the full model is the best by this measurement. Now, the log likelihood addresses fit. It does not address complexity of the model. For AIC, I want the least. Once again, the full, it has the least AIC. The full model is the one I prefer by this measurement. And BIC, the full model is the one I prefer. Now, if I run ANOVA on multiple models, it will sequentially go through and evaluate the hypothesis test that we saw previously. I prefer to do it this way because it explicitly tells me what model is being compared to what. All right, so in a previous video, we talked about the Southern Oscillation Index being lagged by 6 months with recruitment, sorry, led by recruitment by 6 months. And so, or SOI leads recruitment by 6 months is what I want to say. So let's go ahead and build a regression model. This should be a plus sign, where we're taking SOI from 6 months ago to predict the recruitment. All right, and so we're going to set up our data frame this way. So I'm using the time series intersect function with the recruitment and the SOI, but lagged by 6 months. And I'm saying I want a data frame. With that, now I'm building the model. Recruitment depends on SOI from 6 months ago. And so now I've got my linear model, statistically significant. Okay. So now I've been able to pull in a lagged variable into my linear model. Okay. Now you'll notice that this is kind of a pain in the neck to go through this TS intersect. If I look through this whole thing, you might not want to do things exactly this way. So there is a package that will do this a little bit cleaner. And that is the DYNLM package, Dyn linear model package. And this will go ahead and actually run the linear model, where all I have to do is L of my time series and then indicate the lag that I want, L for lag. And then I just put in my time series objects where I need them appropriately. Now, this package, when I load it into RStudio, it automatically loaded and updated a bunch of packages. I don't like that in my system personally. I prefer to, when I load a package, I want to load that package and only the ones it absolutely needs. And I will include more packages if I need to down the road. I don't like having that bazooka package impact personally. Now, this package does rely on a lot of other packages. One of them is the zoo function. To run this function, the linear model function, I needed the merge function for the zoo class. All right, and so that's in the zoo package, naturally. And so just to be able to run this function, I had to pull the merge function for a zoo time series object. All right, so now let's go ahead and take a look at what we've got for our model. So statistically significant, not a great R squared, but there is informative value. Now here's the time series plot of the residuals, and I look at this and I feel like there might be a periodic trend. And when I look at the autocorrelation of the residuals, I visually see a very clear pattern. So clearly we have an autocorrelation on our residuals. There's a problem. I want to address this before I launch this model. And we'll talk about this in another day. All right, well, that's all I've got for you. Life is short. Do math.